How can you prove that something is true for every whole number? There are infinitely many of them, so checking one at a time never finishes. This chapter shows a method that does the whole job in 2 short steps. We also learn how to build things out of smaller copies of themselves. Hello and welcome. Let's start this chapter together. We study a very useful way to prove things. It is called mathematical induction. It lets us prove that something is true for every positive whole number, and we only need 2 small steps. We also learn strong induction, recursive definitions, structural induction, and recursive algorithms. Take your time. Each idea builds on the one before it. This is the plan for the whole chapter, 7 topics in this order. First, mathematical induction. This is our main proof tool. Then strong induction. It gives you more to work with. Then the well-ordering property. Any set of whole numbers that is not empty has a smallest member. Next, recursive definitions. We build objects step by step out of smaller copies. After that, structural induction. It proves facts about objects built that way. Then recursive algorithms. These are procedures that call themselves. The last topic is program correctness. It is not yet in these slides. Now we turn to the first topic, mathematical induction. This is the main tool of the chapter, so let's see how it works. This is the plan for the section, 4 things. First, what mathematical induction is. Then many worked examples, so the method becomes familiar. Then proofs that go wrong, so you can avoid the same mistakes. And last, clear guidelines you can follow every time. Let's start with a picture. Imagine a ladder that goes up forever. We know 2 things. First, we can reach the first rung. Second, if we can reach one rung, then we can reach the next rung. So we reach the first rung, then we reach the second, then the third. We keep going and we reach every rung no matter how high it is. This simple idea is the key to mathematical induction. This is the rule. We want to show that P of n is true for every positive whole number, and we do 2 steps. The basis step, we show that P of 1 is true. The inductive step, we show that P of k implies P of k plus 1 for every positive integer k. In the inductive step, we assume P of k is true. We call that the inductive hypothesis. Then we show that P of k plus 1 must also be true. Think of the ladder again. The basis step reaches rung 1. The inductive step moves us from any rung to the next rung. Together they reach every rung. 3 important points about using induction. First, we can write induction as a rule of inference. If P of 1 is true, and for every k, P of k implies P of k plus 1, then P of n is true for every n here n runs over the positive whole numbers. Second, be careful. We do not assume that P of k is true for all k, we assume it for 1k, and then we show that P of k plus 1 follows. Third, a proof does not have to start at 1. Sometimes it starts at another integer b. We will see examples of that soon. Why is induction correct? It rests on the well-ordering property. That property says every set of positive whole numbers that is not empty has a smallest element. Step 1. Suppose induction fails. Then P of n is false for some n. Collect every such bad n into a set, as this set is not empty. Step 2. Apply the well-ordering property to S, so S has a smallest element. Call it m. Step 3. Can m be 1? No, the basis step says P of 1 is true, so 1 is not bad, so m is bigger than 1. We finish the argument on the next slide. So far, m is the smallest integer with P of m false, and m is bigger than 1. Step 4. Look at the number m minus 1. It is positive, and it is smaller than m since m is the smallest bad number. M minus 1 is not bad, so P of m minus 1 is true. Step 5. Now use the inductive step. P of m minus 1 implies P of m, so P of m is true. Step 6. But m sits in S, so P of m is false. We have said that P of m is both true and false. That cannot happen. So the set S was empty all along. There is no bad number. P of n is true for every positive integer n. This picture also helps you remember. Imagine a long line of dominoes standing up. We number them 1, 2, 3, and so on forever. We knock down the first domino. That is like P of 1 being true. Each domino, when it falls, knocks over the next one. That is like P of k implies P of k plus 1. Let P of n mean the nth domino falls. The first falls, which knocks the second, which knocks the third. In the end, every domino falls. So P of n is true for all positive integers n. Let's prove our first formula. It says the sum of 1, 2, 3, and so on up to n equals n times n plus 1 over 2. Step 1. Write down P of n. It says the sum from I equals 1 to n of I equals n times n plus 1 over 2. Always write this line first. Step 2. The basis step. Put an equal to 1. The right side is 1 times 2 over 2, which is 1. The left side is also 1, so P of 1 is true. Step 3. The inductive hypothesis. Assume the formula holds for k. The sum up to k equals k times k plus 1 over 2. Step 4. Now write down our target. P of k plus 1 says the sum up to k plus 1 equals k plus 1 times k plus 2 over 2. On the next slide we get there. We begin with the sum 1 plus 2 up to k plus the next term k plus 1. Step 1. The first k terms are covered by the hypothesis. Replace them with k times k plus 1 over 2. The extra term k plus 1 stays. Step 2. Put both pieces over the same bottom, which is 2. The top becomes k times k plus 1 plus 2 times k plus 1. Step 3. Both parts of the top share the factor k plus 1. Take it out. We get k plus 1 times k plus 2 over 2. That is exactly what P of k plus 1 claimed. The basis step and this step together prove the formula for every positive integer n. This time nobody hands us the formula. We look for a pattern first. We add the odd numbers one at a time. For n equal 1, the sum is just 1. For n equal 2, 1 plus 3 is 4. For n equal 3, 1 plus 3 plus 5 is 9. For n equal 4, we get 16. For n equal 5, we get 25. Now look down the right column. 1, 4, 9, 16, 25. These are the perfect squares. Once we have this guess, mathematical induction can prove it correct. Let's set the proof up in the same 4 lines as before. Step 1. Write P of n down. It says 1 plus 3 up to 2n minus 1 equals n squared. Step 2. The basis step. For n equal 1, the sum is just 1 and 1 squared is 1, so P of 1 is true. Step 3. The inductive hypothesis. Assume the formula holds at k. The sum up to 2k minus 1 is k squared. Step 4. Write the target. The next odd number after 2k minus 1 is 2k plus 1. So P of k plus 1 says the sum up to 2k plus 1 equals k plus 1, all squared. We start with the sum of the first k odd numbers, plus the next odd number, 2k plus 1. Step 1. The first part is covered by the hypothesis. Replace it with k squared. Step 2. Open the brackets. We have k squared plus 2k plus 1. Step 3. That is a perfect square. It equals k plus 1 all squared. That is exactly P of k plus 1. So the sum of the first n odd numbers is n squared. Induction also proves inequalities. Let's show that n is less than 2 to the n for every positive integer n. Step 1. Write P of n down. It says n is less than 2 to the n. Step 2. The basis step. For n equal 1, 2 to the 1 is 2, and 1 is less than 2, so P of 1 is true. Step 3. The inductive hypothesis. Assume k is less than 2 to the k for one arbitrary positive integer k. Step 4. Write the target. P of k plus 1 says k plus 1 is less than 2 to the k plus 1. The working is on the next slide. We start at k plus 1. Step 1. The hypothesis says k is less than 2 to the k. Swap k for 2 to the k and keep the plus 1. So k plus 1 is less than 2 to the k plus 1. Step 2. Now look at that plus 1. For every positive k, 1 is at most 2 to the k. Replace the 1 with 2 to the k. The value can only grow. Step 3. 2 to the k plus 2 to the k is just 2 times 2 to the k. Step 4. 2 times 2 to the k is 2 to the k plus 1. So k plus 1 is less than 2 to the k plus 1. That is P of k plus 1, and the statement holds for every positive integer n. This example does not start at 1. We show that 2 to the n is less than n factorial, for every integer n at least 4. Step 1. Write P of n down. It says 2 to the n is less than n factorial. Step 2. The basis step starts at 4. 2 to the 4 is 16. 4 factorial is 24. 16 is less than 24, so P of 4 is true. Step 3. The inductive hypothesis. Assume 2 to the k is less than k factorial for some k at least 4. Step 4. Write the target. P of k plus 1 says 2 to the k plus 1 is less than k plus 1 factorial. We start at 2 to the k plus 1. Step 1. Pull out one factor of 2, so it equals 2 times 2 to the k. Step 2. The hypothesis says 2 to the k is less than k factorial. Swap it in. Step 3. Since k is at least 4, k plus 1 is at least 5, which is bigger than 2. So replacing the 2 by k plus 1 only makes the value larger. Step 4. K plus 1 times k factorial is exactly k plus 1 factorial. That is P of k plus 1. Now you can see why we started at 4. For n equals 0, 1, 2, and 3, the claim is false. So the basis step must begin at 4. Now a divisibility proof. We show that n cubed minus n is divisible by 3 for every positive integer n. Step 1. Write P of n down. It says 3 divides n cubed minus n. Step 2. The basis step. For n equal 1, 1 cubed minus 1 is 0. 3 divides 0, so P of 1 is true. Step 3. The inductive hypothesis. Assume 3 divides k cubed minus k. Step 4. Write the target. P of k plus 1 says 3 divides k plus 1. cubed minus k plus 1. We start with k plus 1, cubed minus k plus 1. Step 1. Expand the cube. We get k cubed plus 3k squared plus 3k plus 1, and then we take away k plus 1. Step 2. Now regroup. Put k cubed minus k in one bracket. Everything left over is 3k squared plus 3k, which is 3 times k squared plus k. Look at the two parts. The first part is divisible by 3 by our hypothesis. The second part is 3 times a whole number, so it is divisible by 3 too. A sum of two multiples of 3 is again a multiple of 3. So p of k plus 1 is true, and the proof is done. Now a counting result. A finite set with n elements has 2 to the n subsets, for every whole number n starting at 0. Step 1. Write p of n down. It says a set with n elements has 2 to the n subsets. Step 2. The basis step starts at 0. The empty set has only one subset itself, and 2 to the 0 is 1, so p of 0 is true. Step 3. The inductive hypothesis. Assume every set with k elements has 2 to the k subsets. Step 4. Write the target. Every set with k plus 1 element should have 2 to the k plus 1 subsets. We do that on the next slide. Step 1. Take a set T with k plus 1 elements. Pick one element and call it A, remove it. What is left is a set S with k elements. Step 2. By the hypothesis, S has 2 to the k subsets. Step 3. Take any subset X of S, it gives exactly 2 subsets of T. One is X on its own. Without A, the other is X together with A. Every subset of T is one of these. The picture shows that doubling. Each subset on the left turns into 2 subsets on the right, one without A and one with A. Step 4, so we double the count. T has 2 times 2 to the k subsets, which is 2 to the k plus 1. That is p of k plus 1, and the proof is complete. Now a tiling problem. We start with a big square board, 2 to the n by 2 to the n. We take one square away. We want to cover what is left with L-shaped tiles. A right triamino is that L-shaped tile. It covers 3 squares at once. Turning the tile gives 4 shapes in all. The two pictures show 2 of them. Let's set the proof up on the next slide. The setup takes 3 lines. Step 1. Write p of n down. It says every board of size 2 to the n by 2 to the n, with one square taken away, can be covered by these tiles. Step 2. The basis step. Take n equal 1. That is a 2 by 2 board. Remove any one of its 4 squares. The 3 squares that are left form an L1 tile covers them, so p of 1 is true. Step 3. The inductive hypothesis. Assume every board of size 2 to the k by 2 to the k works. We finish on the next slide. Step 1. Take a board of size 2 to the k plus 1 by 2 to the k plus 1. Cut it in half across and in half down. That gives 4 smaller boards, each 2 to the k by 2 to the k. The left picture shows the cut, 4 equal quarters. Step 2. One of the 4 quarters holds the square we already removed. By our hypothesis, that quarter can be tiled. Step 3. The other 3 quarters are still complete. From each one, remove the corner square that touches the center of the big board. Now each of the 3 is a board with one square missing, so the hypothesis tiles all 3. Step 4. Look at the 3 squares we just took out. They sit around the center and form an L1 triamino covers them. The right picture shows that center tile in place. Every square of the big board is now covered. so P of k plus 1 is true. Be careful with this one. It looks like a proof, but it is wrong. The claim is that any set of lines in the plane with no two parallel all meet at one common point. That is clearly false, so one of the steps below must be bad. See if you can spot it. Step 1. Write P of n down. It says that any n lines in the plane with no two parallel all pass through one common point. Step 2. The basis step uses n equal 2. Two lines that are not parallel do cross at one point, so P of 2 is true. That part is fine. Step 3. The inductive hypothesis. Assume P of k for some k at least 2. Any k such lines share one point. Step 4. The target. Any k plus 1 such lines should share one point. The working is on the next slide. Step 1. Take k plus 1 lines, all different, no two parallel. Look at the first k of them. The hypothesis says they share one point. Call it P1. Step 2. Now look at the last k lines. The hypothesis says they share 1.2. Call it P2. Step 3. The argument now claims P1 and P2 are the same point. The reason offered is this. If they were different, then two of our lines would pass through both points. 2 points fix one line, so those two lines would be the same line. That breaks distinctness. Step 4. So the argument concludes that P1 equals P2 and that this single point lies on all k plus 1 lines. The conclusion is absurd, so one of these steps is bad. The next slide names it. Step 3 is the bad step. To force P1 and P2 together, we need two of the lines to belong to both groups. That only happens when k is 3 or more. Look at the case where k is 2. There are 3 lines in all. The first group is lines 1 and 2. They meet at P1. The last group is lines 2 and 3. They meet at P2. The only line in both groups is line 2. One shared line passes through many points, so P1 and P2 can sit anywhere along it. Nothing forces them together. Now take k at least 3. There are 4 lines or more. The two groups then share at least 2 lines. 2 different lines cross at exactly one point, so P1 and P2 really must be the same point. So the inductive step is fine from k equal 3 onwards, but P of 2 does not give P of 3. The chain breaks at its very first link, and a chain that never starts proves nothing. Let's collect the steps into one clean template. This is the first half. Step 1. Put the claim in a fixed shape. For all n greater than or equal to b, P of n here b is the starting integer. Step 2. Write the words basis step. Then show P of b is true. Check that you use the right value of b. Step 3. Write the words inductive step. Step 4. State the inductive hypothesis clearly. Assume P of k is true for one arbitrary fixed integer k, at least b. Now the second half of the template. Step 5. Write out exactly what P of k plus 1 says. That line is your target. Step 6. Prove P of k plus 1. Using P of k, then check the argument again for the small values of k, including k equal b, that is where the line's proof failed. Step 7. Say clearly that the inductive step is done. Step 8. Give the final conclusion. By mathematical induction, P of n is true for all integers and at least b. Follow these 8 steps, and your proof will be complete and correct. Now we turn to a stronger tool called Strong Induction. It comes with a partner idea, the well-ordering property. This is the plan for the section, 4 things. First, what strong induction is. Then several example proofs that use it. There is also a use in computational geometry, but that part is not on these slides. And last, the well-ordering property. Strong induction has the same 2 steps as before. We still want p of n for every positive integer n. The basis step is the same. We check p of 1. The difference is in the inductive step. Here you may assume every case up to k you assume p of 1, and p of 2, and so on, up to p of k. From all of that you prove p of k plus 1. The method also goes by 2 other names. The second principle of mathematical induction and complete induction. Let's put the 2 methods side by side. The basis step is the same in both. Show p of 1. The middle row is the difference. In ordinary induction you may assume only p of k, the case just below. In strong induction you may assume every case from p of 1 up to p of k. The bottom row is the same again. Either way, you must prove p of k plus 1. So strong induction gives you more to work with. Use it when the new case depends on a case far below k, not just the one before it. Let's picture a tall ladder again. Let p of n mean we can reach rung n. We reach every rung if 2 things hold. First, we can reach the first rung. Second, for every integer k, if we can reach the first k rungs, then we can reach rung k plus 1. So the basis step says p of 1 holds. The inductive step assumes we can reach all of the first k rungs. That is p of 1, and p of 2, and so on up to p of k. From that we show we can reach rung k plus 1. Put together, we reach every rung of the ladder. A nice example. We can reach rungs 1 and 2 of an infinite ladder, and from any rung we can climb 2 rungs higher. Ordinary induction is hard here, because reaching rung k does not by itself give rung k plus 1. The jump is 2 rungs, not 1. Strong induction fits. Step 1, write p of n down. It says we can reach rung n. Step 2, the basis step. We are told we can reach rung 1 and rung 2, so p of 1 and p of 2 both hold. Step 3, the hypothesis. Assume we can reach every rung from 1 up to k, where k is at least 2. Step 4, now pick one case out of that hypothesis. We choose rung k minus 1. Since k is at least 2, that rung is in our range, so we can reach it. Step 5. From rung k minus 1 we climb 2 rungs higher. That lands us on rung k plus 1, so we reach every rung of the ladder. Which method should you pick? You may always use strong induction in place of ordinary induction, but if the ordinary proof is simpler, use that one. These 3 ideas are equivalent. Mathematical induction, strong induction, and the well-ordering property all have the same power. Sometimes one of them makes a proof easy while the other 2 look hard, so it helps to know all 3. Now we finish an important proof from Chapter 4. Every integer bigger than 1 can be written as a product of primes. Step 1, write p of n down. It says n can be written as a product of primes. Step 2, the basis step. Check p of 2. 2 is prime, so it is a product of 1 prime, true. Step 3, the hypothesis. This is where we need strong induction. Assume p of j holds for every j from 2 up to k. Step 4, the target. We must show k plus 1 is a product of primes. The next slide splits it into 2 cases. Case 1. Suppose k plus 1 is prime, then it is already a product with just one factor. We are done at once. Case 2. Suppose k plus 1 is composite. Then we can split it into two positive factors a times b, where a is at least 2 and both a and b are smaller than k plus 1. Now look at the range. Both a and b sit between 2 and k. That is exactly the range our hypothesis covers. So each of them is a product of primes. Multiply the two lists of primes together. The product is k plus 1. So k plus 1 is a product of primes, and the proof is done. Section 4.3 proves the other half of the theorem. The prime factorization of a number is unique. A stamps example. We have only 4 cent stamps and 5 cent stamps. We want to make any postage of 12 cents or more. Let P of n mean we can make n cents from these two stamps. The basis step here checks 4 values, not 1. You will see why in a moment. 12 cents is 3 4-cent stamps. 13 cents is 2 4-cent stamps and 1 5-cent stamp. 14 cents is 1 4-cent stamp and 2 5-cent stamps. 15 cents is 3 5-cent stamps. Step 1. The hypothesis. Assume P of j for every j from 12 up to k, where k is at least 15. Step 2. Now reach back 3 places. Look at k minus 3. Since k is at least 15, k minus 3 is at least 12, so that case is inside our hypothesis. We can make k minus 3 cents. Step 3. Take that pile of stamps and add one more 4-cent stamp. The total goes up by 4, so we get k minus 3 plus 4, which is k plus 1 cents. Step 4. So P of k plus 1 holds, and P of n holds for every n at least 12. Now you can see why the basis step needed 4 values. The step reaches back 3, so it needs 4 starting cases in place. Now we prove the same stamps result with ordinary induction. The basis step makes 12 cents with 3 4-cent stamps. The hypothesis assumes P of k for some k at least 12. So we hold some pile of stamps worth k cents, and we must push the total up by exactly 1 cent. Case 1. Suppose the pile uses at least one 4-cent stamp. Swap that stamp for a 5-cent stamp. We lose 4 and gain 5, so the total goes up by 1. Case 2. Suppose the pile uses no 4-cent stamps at all. Then it is all 5-cent stamps, and it is worth 12 cents or more, so it holds at least 3 of them. Take 3 of those 5-cent stamps out and put 4 4-cent stamps in. 3 5s is 15. 4 4s is 16. So again the total goes up by 1. Either way we make k plus 1 cents. Now we meet the well-ordering property. It says something simple. Take any set of non-negative integers that is not empty. Then that set has a smallest element. This is one of the basic axioms for the integers. We can use it straight away inside a proof, as we will see next. We can also make it more general. A set is called well-ordered if every non-empty subset of it has a least element. We must say non-empty, because the empty subset has no elements at all, so it can have no least one. The natural numbers are well-ordered under the usual, less than or equal order. Finite strings are well-ordered too, but we must order them with care. Sort them by length first and then alphabetically. Plain dictionary order will not do. Look at the strings 1, 0, 1, 0, 0, 1, and so on. Each one is smaller than the one before it, so that set has no least string. This proof uses the well-ordering property directly. We prove the division algorithm. Given an integer and a positive integer d, we want a quotient q and a remainder r. Step 1. Build a set S, put into it every non-negative number of the form a minus d times q, where q runs over all the integers. These are the possible remainders. Step 2. Check that S is not empty. Choose q very negative. Then minus d times q grows without limit, so a minus dq is certainly non-negative for some q. Step 3. Apply the well-ordering property. Since S is a non-empty set of non-negative integers, it has a smallest element. Call it R, equal to a minus d times q sub 0. Step 4. Move terms across. We get a equals d times q sub 0 plus r, and r is at least 0. One thing is still missing. We must show r is smaller than d. Now we show the remainder is smaller than d. Suppose it is not. Suppose r is at least d. Then look at the next candidate, the one we get by using q sub 0 plus 1. Step 1. Multiply out. A minus d times q sub 0 plus 1 is a minus dq sub 0 minus d. Step 2. But a minus dq sub 0 is exactly r, so the value is r minus d, and since we supposed r is at least d, this is still 0 or more. So r minus d belongs to S, but r minus d is smaller than r, and r was supposed to be the smallest element of S. That cannot happen. So our supposition was wrong, and r is smaller than d uniqueness of q, and r is exercise 37. Now we turn to a new idea called recursion. A recursive definition builds a thing out of smaller copies of the same thing. This is the plan for the section, 4 things. First, we define functions step by step. Second, we define sets step by step. Third, structural induction. It proves facts about sets built by recursion. And last, generalized induction, a wider version of the same idea. A recursive definition of a function has 2 parts. The basis step gives the value at 0. Sometimes it must give more than that. If the rule reaches back 2 steps, the basis must give the first 2 values. The Fibonacci numbers, later in this section, need both f of 0 and f of 1. The recursive step tells you how to get the value at a number from the values at smaller numbers. Think of a function f of n as a sequence of 0, a 1, a 2, and so on. The value f of I is just a sub-IVIS is the same idea as a recurrence relation. Let's work the first example. We know f of 0 is 3. The rule says f of n plus 1 equals 2 times f of n plus 3. So f of 1 is 2 times 3 plus 3. That is 9. Now f of 2 uses the answer we just found. 2 times 9 plus 3, that is 21. Then f of 3 is 2 times 21 plus 3, that is 45. And f of 4 is 2 times 45 plus 3, that is 93. Notice the pattern of work. Each line reuses the line above it. That is what recursion means. Now let's define the factorial function by recursion. Step 1. The basis step gives the value at 0. By convention, 0 factorial is 1, so f of 0 is 1. Step 2. The recursive step builds the next value from the one before. N plus 1 factorial is n plus 1 times n factorial. Step 3. Let's check it on a small case. F of 3 is 3 times f of 2, which is 3 times 2 times f of 1, which is 3 times 2 times 1 times f of 0. That is 6, and 3 factorial is 6. It works. We can also define a sum by recursion. Step 1. The basis step takes the shortest sum. The sum from k equals 0 to 0 of a sub k is just a sub 0. Step 2. The recursive step adds one more term. The sum up to n plus 1 equals the sum up to n plus the next term, a sub n plus 1. Step 3. Let's check it. For n equal 2, the rule unfolds to the sum up to 1 plus a sub 2. The sum up to 1 unfolds again to a sub 0 plus a sub 1. So we get a sub 0 plus a sub 1 plus a sub 2. That is right. Each new sum reuses the sum before it. These are the famous Fibonacci numbers. There are two basis values. F sub 0 is 0 and F sub 1 is 1. The recursive step says every later number is the sum of the two before it. So F sub 2 is F sub 1 plus F sub 0. That is 1 plus 0, which is 1. F sub 3 is F sub 2 plus F sub 1. That is 1 plus 1, which is 2. F sub 4 is F sub 3 plus F sub 2. That is 2 plus 1, which is 3. F sub 5 is F sub 4 plus F sub 3. That is 3 plus 2, which is 5. In Chapter 8, we use these numbers to model how rabbits grow in number. Next, we prove a fact about them with strong induction. Alpha here is 1 plus the square root of 5, all over 2. We show that f sub n is greater than alpha to the power n minus 2 whenever n is at least 3. Step 1. Write p of n down. It says f sub n is greater than alpha to the power n minus 2. Step 2. The basis step. Check p of 3. Alpha is about 1.6, so alpha is less than 2, and 2 is f sub 3. Step 3. We check p of 4 as well because the inductive step will reach back two places. Alpha squared is 3 plus root 5 over 2, which is about 2.6. That is less than 3, and 3 is f sub 4. Step 4. The hypothesis. Assume the claim for every j from 3 up to k, where k is at least 4. Step 5. The target. We must show f sub k plus 1 is greater than alpha to the k minus 1. This is the key trick of the whole proof. Alpha solves the equation x squared minus x minus 1 equals 0. So alpha squared equals alpha plus 1. Take our target power, alpha to the k minus 1. Step 1. Split off two factors of alpha. That leaves alpha squared times alpha to the k minus 3. Step 2. Now swap alpha squared for alpha plus 1. Step 3. Multiply out the bracket. Alpha times alpha to the k minus 3 is alpha to the k minus 2, and 1 times alpha to the k minus 3 is itself. So the target power breaks into two pieces, and that shape matches the Fibonacci rule. Now we finish. Since k is at least 4, both k and k minus 1 sit inside the range of our hypothesis. So f sub k is greater than alpha to the k minus 2, and f sub k minus 1 is greater than alpha to the k minus 3. We start at f sub k plus 1. Step 1. The Fibonacci rule says it equals f sub k plus f sub k minus 1. Step 2. Replace each of those two using the hypothesis. The sum is greater than alpha to the k minus 2 plus alpha to the k minus 3. Step 3. But we just showed that sum is exactly alpha to the k minus 1. So f sub k plus 1 is greater than alpha to the k minus 1. That is p of k plus 1, and the proof is complete. This theorem is about the Euclidean algorithm, our method for the greatest common divisor. It says the number of divisions is at most 5 times the number of decimal digits in B. Gabriel Lamé proved it in the 19th century. Let's walk through the proof. Run the algorithm on an B, with at least B renamed as R0 and B as R1. Say the run takes n divisions. The first division divides R0 by R1. It leaves a quotient Q1 and a remainder R2, which is smaller than R1. The second division does the same one place along. It leaves the remainder R3, smaller than R2. The pattern repeats down the chain. The second to last division leaves the remainder R sub n. The last division comes out even. Its remainder is 0, so the algorithm stops there. The next slide turns this chain into Fibonacci numbers. Take a strictly bigger than b for this part. If a equals b, the algorithm stops after one division, and one division is certainly within the bound. Now look at the quotients. Every quotient from q1 to qn minus 1 is at least 1. The last quotient, q sub n, is at least 2, because r sub n is strictly smaller than r sub n minus 1. Line 1. The last remainder r sub n is a positive whole number, so it is at least 1, and 1 is f sub 2. Line 2. R sub n minus 1 equals r sub n times q sub n, and q sub n is at least 2, so it is at least twice f sub 2, which is f sub 3. Line 3. R sub n minus 2 equals r sub n minus 1 times a quotient of at least 1, plus r sub n, so it is at least the sum of the two below it, which is f sub 3 plus f sub 2, that is f sub 4. Each line up repeats the same move, and the Fibonacci index climbs by 1. At the top, b, which is r1, is at least f sub n plus 1. Now we turn that Fibonacci bound into a statement about digits. We showed b is at least f sub n plus 1. Line 1. Example 4 said f sub n plus 1 is greater than alpha to the n minus 1, for n bigger than 2. So b is greater than alpha to the n minus 1. Line 2. Take base 10 logs of both sides. The log of b is greater than n minus 1 times the log of alpha. Line 3. The log of alpha is about 0.208, which is more than 1/5. So the right side is more than n minus 1 over 5. Line 4. Multiply across by 5 and move terms. We get n minus 1 is less than 5 times the log of b. Now say b has k decimal digits. Then b is smaller than 10 to the k, so the log of b is smaller than k. Line 0. We had n minus 1 is less than 5 times the log of b. Line 1. Replace the log of b by k, the bound only grows, so n minus 1 is less than 5k. Line 2. Both n and k are whole numbers, so n is at most 5k. That is exactly what the theorem claimed. One gap is left. We use the Fibonacci bound only for n bigger than 2. The short runs need no work. If n is 1 or 2, then n is at most 5, and 5k is at least 5, because b has at least one digit. As a result, the number of divisions grows like the log of b. This was the very first result in the field we now call computational complexity. We build sets by recursion too. The definition has 2 parts. The basis step lists some starting elements. The recursive step tells you how to make new elements from ones you already have. There is also a quiet third rule, the exclusion rule. It says nothing else is in the set. Only what the 2 steps produce belongs. We always assume this rule. Soon we prove facts about these sets using structural induction. The first example, builds a set S of integers. The basis puts the number 3 into S. The rule says if x and y are in S, then x plus y is in S. So 3 is in S, then 3 plus 3 is 6. Then 3 plus 6 is 9. We get all the positive multiples of 3. The second example builds the natural numbers. The basis puts 0 in. The rule says if n is in, then n plus 1 is in. That gives 0, 1, 2, and every whole number. A string is a row of symbols from an alphabet. We write the set of all strings as sigma star. The basis says the empty string called lambda is a string. The recursive step says if W is a string and X is one symbol, then W followed by X is a string. If the alphabet is 0 and 1, then sigma star holds every bit string. On the next slide, we build one string, step by step. Let's build the string of a B, one symbol at a time. Each line uses the rules once. Step 1. The basis step gives us the empty string lambda. Step 2. Take the empty string and add the symbol A on the end. That gives the string A. Step 3. Take the string A and add another A that gives a A. Step 4. Take a A and add a B that gives it a B, so a B is in sigma star. Notice how the string grows from the right, one symbol per rule. Concatenation joins two strings into one. We write it with a dot. The basis says joining any string W with the empty string gives back W. The recursive step handles a longer second string. If the second string ends in the symbol X, join the front parts first, then add X at the end. We usually drop the dot and just write the two strings side by side. For example, Abra joined with cadabra gives abracadabra. We can define the length of a string by recursion too. Step 1, the basis step. The empty string has no symbols at all, so its length is 0. Step 2, the recursive step. Take a string W and add one symbol X on the end. The length of WX is the length of W plus 1. Step 3. Let's check it on the string of B. Its length is the length of A plus 1. The length of A is the length of the empty string plus 1, which is 1. So the answer is 2, and a B does have two symbols. Now the set P of balanced parentheses. The basis puts one match pair, open then close, into P. The recursive step makes new strings from old ones. Take a string W and P and wrap it in a pair, or take two strings W and X and P and write them side by side. Those two rules give every balanced string. Now let's build one string. Step 1. The basis step gives us one pair. Step 2. Use the second rule, W followed by X, with both of them that one pair. We get two pairs side by side. Step 3. Use the first rule, wrap W in a pair, with W being those two pairs. We get the string we wanted, so it is in P. Now think about the string close, close, open, open. Why can it never be in P? Let's check every rule and ask what the first symbol can be. The basis gives one pair. Its first symbol is an open parenthesis. The first rule wraps W inside a pair, so the string starts with an open parenthesis again. The second rule writes W and then X, so the first symbol is whatever W started with, and W is already in P. So every rule gives the same answer. Every string in P starts with an open parenthesis. Our string starts with a close parenthesis, so nothing can build it. It is not balanced. Last, we define well-formed formulae in logic. The basis says three things are formulae on their own: true, false, and any single variable s. The recursive step combines two formulae E and F. You may negate E, or join E and F with and with or with if, then or with if and only if, always inside parentheses. For example, open P or Q, then arrow, then Q and false all wrapped up is well formed. But PQ and written in that order is not. The rules never put two variables next to each other, and the operator and must sit between two formulae, never after them. Only the not sign is different. It goes in front of a single formula. Let's define a rooted tree. A rooted tree is a set of dots called vertices, joined by lines called edges. One special vertex is the root. The basis step is simple. One single vertex, R, is a rooted tree by itself. The recursive step lets us grow bigger trees. Suppose we already have some rooted trees. They share no vertices, and each one has its own root. Now take a brand new vertex R, draw an edge from R down to the root of each old tree. The result is a new, taller rooted tree with R at the top. The basis step is one lonely vertex. In step 1, we take that single vertex and put a new root above it. We can give the new root one child, two children, or three children. Each result is a rooted tree. In step 2, we do the same thing again. We take the trees from step 1 and put a new root on top. Now the trees get taller. We can keep going forever this way. Trees are studied in much more detail later in Chapter 11. Next, we look at one special kind of tree, the full binary tree. Now we define full binary trees. In a full binary tree, every vertex that is not a leaf has exactly two subtrees. The basis step is the same as before. One single vertex, R, is a full binary tree. The recursive step joins two of them. Suppose we have two full binary trees, T sub 1 and T sub 2, with no shared vertices. We add a new root R. We draw one edge to the root of T sub 1, the left subtree. We draw one more edge to the root of T sub 2, the right subtree. The result is a full binary tree. Let's build full binary trees step by step. The basis step is one single vertex. In step 1, we join two single vertices under a new root. This gives a root with two leaves. It is the smallest full binary tree that is not just a point. In step 2, we join two of the step 1 trees, or a point and a step 1 tree under a new root. Each time we add a new root, we give it exactly two subtrees. That is why every internal vertex always has two children. Here we build a set S. We put the number 3 into S then, whenever two numbers x and y are in S. We also put their sum into S. Let it be the set of positive multiples of 3. To prove the two sets are equal, we show each one sits inside the other. Part 1 shows a sits inside S. Let P of n say that 3n is in S. Step 1, the basis step. 3 times 1 is 3, and the first rule puts 3 into S. Step 2, the inductive hypothesis. Assume 3k is in S. Step 3, now use the second rule. Take x equal to 3k and y equal to 3. Both are in S, so their sum is in S. Step 4, 3k plus 3 is 3 times k plus 1, so P of k plus 1 holds. Part 2 is on the next slide. Part 2. We show S sits inside A. The idea is to check that no rule can ever put a number outside A into S. Step 1. The basis step. The only starting element is 3. and 3 is 3 times 1, so it is a multiple of 3. Step 2, the recursive step. Assume the two numbers we are combining, x and y, are already multiples of 3. Step 3, Theorem 1, Part 1, from Section 4.1 says that a sum of two multiples of 3 is a multiple of 3, so the new element is also a multiple of 3. Both directions hold, so the two sets are equal. Here we used ordinary induction on a set built by recursion. Next, we meet a more direct tool called structural induction. Structural induction is made for sets built by recursion. It has two steps that match the two parts of the recursive definition. In the basis step, we check the property for the starting elements, the ones named in the basis of the definition. In the recursive step, we look at how new elements are built from old ones. We assume the property is true for each old piece. Then we show it stays true for the new element built from those pieces. If both steps work, the property holds for every element in the set. This works because structural induction follows from ordinary mathematical induction. We measure full binary trees with two more recursive definitions. The first one is the height, written h of t. For a single root, the height is 0 because there is nothing below it. When we join two trees t sub 1 and t sub 2 under a new root, the new height is 1 plus the larger of the two old heights. We add 1 for the new top level, and we take the taller side. The second one is the number of vertices, written n of t. For a single root, there is just one vertex. When we join two trees, we count 1 for the new root, plus all the vertices in t sub 1, plus all the vertices in t sub 2. This theorem is about full binary trees. It says the number of vertices, n of t, is at most 2 to the power h of t plus 1, minus 1. In words, a tree of a given height can hold only so many vertices. We prove it by structural induction. Step 1. The basis step checks a single root. Their n of t is 1 and h of t is 0. 2 to the power 0 plus 1 minus 1 equals 1. 1 is at most 1, so the bound holds. Step 2. The recursive step. We build t from two smaller trees. Assume the bound already holds for the left subtree t sub 1. Step 3. Assume it for the right subtree t sub 2 as well. On the next slide we combine them. We start from the vertex count. N of t equals 1 plus the vertices of the left subtree plus the vertices of the right subtree. Step 1. Replace each subtree count by its assumed bound. The plus 1 at the front cancels one of the two minus 1s, so a single minus 1 is left. Step 2. Each of the two powers is at most the larger of the two, so the sum is at most twice the larger power, minus 1. Step 3. A handy rule helps here. The larger of 2 to the x and 2 to the y is 2 to the larger of x, and y, so the exponent becomes the max of the two heights, plus 1. Step 4. But the recursive formula for height says that max plus 1 is exactly h of t. Step 5. And 2 times 2 to the h of t is 2 to the h of t plus 1. That is the bound we wanted. The recursive step is done, so the bound holds for every full binary tree. Generalized induction is a bigger version of induction. It works on many kinds of sets, not just the whole numbers. The set only needs the well-ordering property, which we study in Chapter 9. A good example is the lexicographic ordering on pairs of natural numbers. This is like dictionary order. To compare two pairs, first look at the first numbers. If they differ, the pair with the smaller first number comes first. If the first numbers are equal, we then compare the second numbers. Strings of letters use the same rule, letter by letter. In the next example, we use this ordering to prove a fact about a sequence with two indexes. This example has a sequence with two indexes, m and n. It starts at a sub-zero 0, which equals 0. The recursive rule has two cases. If n is 0 and m is bigger than 0, then a sub-mn equals a sub-m minus 1n plus 1. If n is bigger than 0, then a sub-mn equals a sub-m, n minus 1 plus n. We want to prove a closed formula. It says a sub-mn equals m plus n times n plus 1 over 2. The basis step checks the pair 0, 0. Both sides come out 0. The inductive step assumes the formula for every pair that comes earlier in dictionary order. The two cases are worked on the next slide. Take the first case. Here n is 0 and m is bigger than 0. The pair m minus 1 n comes earlier in dictionary order. We start at a sub-mn. Step 1. The rule says a sub-mn equals a sub-m minus 1n plus 1. Step 2. The hypothesis applies to that earlier pair. Swap in the formula. We get m minus 1 plus n times n plus 1 over 2 plus 1. Step 3. The minus 1 and the plus 1 cancel. What is left is m plus n times n plus 1 over 2. That is exactly the formula we claimed. Now the second case. Here n is bigger than 0, and the pair m, n minus 1, comes earlier. We start at a sub-mn again. Step 1. The rule says a sub-mn equals a sub-m, n minus 1 plus n. Step 2. The hypothesis applies to that earlier pair. Put its formula in. We get m plus n times n minus 1 over 2 plus n. Step 3. Put the last two terms over the same bottom. N times n minus 1 plus 2n is n times n plus 1. So we get m plus n times n plus 1 over 2. Both cases give the formula, so it holds for every pair of natural numbers. Now we turn to recursive algorithms. A recursive algorithm solves a problem by calling itself on a smaller version of the same problem. This is the plan for the section, 4 things. First, what a recursive algorithm is. Then we prove that a recursive algorithm gives the correct answer. The text also compares recursion with iteration, and we leave that comparison to your reading. And last, merge sort, a fast way to sort a list. An algorithm is recursive when it solves a problem by using a smaller copy of the same problem. Each step makes the input smaller. The input must reach a starting case that we already know how to solve. If it does not, the algorithm never stops. So every recursive algorithm needs a known base case. Let's compute n factorial with recursion, where n is a whole number, 0 or more. We use the recursive definition of the factorial. If n equals 0, we return 1. That is the base case. Otherwise, we return n times factorial of n minus 1. So the algorithm keeps calling itself with a smaller number until it reaches 0. Now let's compute it to the power n. Here is a non-zero real number, and n is a whole number, 0 or more. If n equals 0, we return 1, because any non-zero number to the power 0 is 1. Otherwise, we return a times power of n minus 1. Each call lowers the exponent by 1 until it reaches 0. Let's find the greatest common divisor of A and B, with a smaller than B. We use two facts. The greatest common divisor of A and B equals the greatest common divisor of B mod A, and A also, the greatest common divisor of 0 and B is B when B is positive. So if A equals 0, we return B. Otherwise, we return the greatest common divisor of B mod A, and A here B mod A means the remainder when B is divided by A. Now let's compute B to the power n. Mod m, this is a fast method. If n equals 0, we return 1. If m is even, we compute the power for half of n, square it, then take mod m. If n is odd, we do the same for the floor of n over 2, square it, take mod m, then multiply by b mod m, and take mod m again. Splitting n in half each time makes this much faster than multiplying b by itself n times. Let's search a sorted list with recursion. The list runs from position I to position j, and we are looking for x at the start I is 1 and j is n. We look at the middle position m, the floor of I plus j over 2. If x equals a sub m, we found it, and we return m. If x is smaller than a sub m, we search the left half, from I to m minus 1. If x is larger, we search the right half, from m plus 1 to j. If none of these hold, x is not in the list, and we return 0. Each call cuts the list in half. Induction and strong induction can show that a recursive algorithm always returns the right answer. Let's prove that the power algorithm is correct. The code is at the top. If n is 0, it returns 1. Otherwise, it returns a times the call power of n minus 1. Step 1. Write p of n down. It says the call power of n returns to the n. Step 2, the basis step. When n is 0, the code returns 1, and any non-zero number to the power 0 is 1, so p of 0 is true. Step 3, the inductive hypothesis. Assume the call power of an k returns to the k. The working is on the next slide. We ask what the code returns when n is k plus 1. That is not 0, so the code takes the else branch. We start at the call power of n k plus 1. Step 1. The else branch returns a times the call power of n k. Step 2. Our hypothesis tells us what that inner call returns. It returns to the k. Step 3. So the whole thing is a times a to the k, which is a to the k plus 1. That is p of k plus 1. So the algorithm returns the right answer for every whole number n. Let's meet merge sort. It splits a list into two halves. If the length is odd, one half gets one more element than the other. It keeps splitting until each piece holds just one element. This splitting draws a balanced binary tree. The two halves come out exactly equal at every step only when the length is a power of 2. A list of 10 splits into 5 and 5, and 5 is odd. Then merge sort merges the pieces back together in pairs, always keeping them sorted. It keeps merging until one sorted list remains. This merging also draws a binary tree. Let's sort the list 8, 2, 4, 6, 9, 7, 10, 1, 5, 3. Step 1. Merge sort splits the list as evenly as it can. 10 splits into 5 and 5. 5 splits into 3 and 2. It keeps going the same way. Step 2. The splitting stops when every element sits alone. That gives 10 tiny lists, and a list with one element is already in order. Step 3. Now the pieces come back together in pairs. Each merge keeps the results sorted. The merged lists have length 2, then 3, then 5. Step 4. We stop when one list is left. It holds the numbers 1 through 10 in order. The picture on the next slide shows the whole run. This picture shows the whole run. Read the top half downward. The list splits again and again until each element sits alone in the middle row. Now read the bottom half upward. Pairs of sorted pieces merge together step by step. Each row holds fewer lists than the one above it, and each list in it is longer. At the very bottom sits the full sorted list. Let's write merge sort as a recursive algorithm for a list L of n elements. If the list has more than one element, we find the middle position m, the floor of n over 2. We split L into a left half, L1, and a right half, L2. We sort each half by calling merge sort again. Then we merge the two sorted halves into one sorted list. If the list has just one element, it is already sorted. The merge subroutine joins two sorted lists into one sorted list. While both lists still have elements, we compare their first elements. We take the smaller one and put it at the right end of the new list. If the two are equal, we must say which one to take, so we take the one from L1. If one list becomes empty, we copy the rest of the other list. To merge a list of m elements with a list of n elements, we need at most m plus n minus 1 comparisons. Let's merge the list 2, 3, 5, 6 with the list 1, 4. At the start, the first list is 2, 3, 5, 6, and the second list is 1, 4. We compare the two front values. 1 is less than 2. So 1 moves into the merged list. Now the front values are 2 and 4. 2 is smaller. 2 moves across. Now we compare 3 and 4. 3 is smaller. 3 moves across. Now 4 is smaller than 5. 4 moves across, and the second list is now empty. So we copy the rest of the first list, 5 and 6. The merged list is 1, 2, 3, 4, 5, 6. The number of comparisons needed to merge sort a list of n elements is big, O of n log, and let's count them. To keep it simple, assume n is a power of 2. So n equals 2 to the m, the splitting builds a binary tree with m levels. Step 1. At the bottom level m, there are 2 to the m lists, and each holds one element. Step 2. Look at any level k, there are 2 to the k lists there, and each holds 2 to the m minus k elements. Step 3. Merging those lists in pairs gives level k minus 1. Half as many lists, each twice as long. Step 4. Now the cost. Earlier we saw that merging a list of m elements with a list of n elements takes at most m plus n minus 1 comparisons. Here both halves have 2 to the m minus k elements. So one merge costs at most 2 to the m minus k plus 1, minus 1. Now we add up the comparisons over all the levels. At level k there are 2 to the k minus 1 merges, and each costs at most 2 to the m minus k plus 1, minus 1. Multiply, and sum over k from 1 to m. Line 1. Multiply the bracket out. The first piece is 2 to the k minus 1 times 2 to the m minus k plus 1. The exponents add to m, so that piece is just 2 to the m. The same for every k, the second piece is 2 to the k minus 1. Line 2. The first sum has m equal terms, so it is m times 2 to the m. The second sum is a geometric series from section 2.4, and it equals 2 to the m minus 1. Line 3. Now put m equal to log n, and 2 to the m equal to n, we get n log n, minus n plus 1. So merge sort uses big O of n log n comparisons. That is an upper bound. On its own, it does not say merge sort is the best. Chapter 3 gives the counting argument for a lower bound as well. Every sort that works by comparing elements needs at least a constant times n log n comparisons in the worst case. The two bounds match, so merge sort is best possible, up to a constant factor.